In this video, we will learn about mass spectrometry and how it is used to try to estimate or guess the molecular formula of a given sample. So let's first look at how exactly mass spectrometry works. In mass spectrometry, or MS, what we're measuring is the mass to charge ratio of an ion. And again, usually the purpose is to determine the chemical formula of a given substance, so molecules in a given substance. So there's a few pieces in the instruments that are used to measure mass spectra, which are called mass spectrometers. So the first thing is that our molecules that we're studying are usually neutral. And so our first step is that we have to ionize these molecules and also get them into the gas phase so that they're kind of completely isolated from everything else, so that really we're only measuring one ion at a time, not some larger kind of cluster of ions. So there's many different forms of ionization. One common one is called electron ionization. This is a relatively harsh method, and what happens is, given a neutral molecule, the instrument will fire a beam of high energy electrons at your sample, and that will kind of knock some electrons off of the molecule, generating some radical ion species and kind of loose electrons that have been knocked off. There are other softer types of ionization techniques, but a discussion of those is probably better suited to an instrumental analysis course. So in the mass spectrometer, usually the idea is that you make these ions, they're kind of in the gas phase, and then you accelerate them to be about the same kinetic energy and have them kind of travel down some sort of a tube. And as they're traveling down the tube, this beam of ions will be kind of focused, so it's a very narrow beam of ions going through the tube. Then that beam will be deflected using a large magnet, and because of the differing sizes and masses and charges of these ions, that deflection will depend on this ratio of mass to charge. And the general trend is that the heavier the ion is, the less it will get deflected. Maybe that makes a little sense if you just think about trying to deflect a heavy object moving through space. And then the other trend is that if the ion is more highly charged, then it is easier to deflect, which also makes sense, because if an ion has a lot of charge, it should feel the magnet a lot more. Then as this ion beam is deflected, what this 0.3 tells you is that some of the ions will be deflected more and some of them will be deflected less. And only ions that are all the exact same mass to charge ratio will be deflected the same amount. So then what we're doing is that there's a detector at the end of the tube that is counting the ions as they arrive, but it was only able to count the ions that have been deflected in a way such that they actually hit the detector. So to give you kind of an image of what this looks like, I tried to color code the ion beams in here. So the heavier purple ions here are so heavy they aren't very deflected by the magnet, so they kind of just run into the side of the tube here. The pink ones are kind of the ideal size or mass to charge ratio, and those are the only ones that get to the detector. And then the teal ones are too highly charged, let's say, so they're deflected significantly and kind of hit the other side of the tube. So then, in order to collect data, what we need to do is to scan a range of values, so a range of magnet values, with the goal of then getting the various different ion beams to hit the detector. So that might look like this, right? Let's say I increase the strength of my magnet. That would cause that purple, pink, and teal to all deflect more, and in the end only focus the purple ion beam onto the detector. And so in an actual instrument, you would have to calibrate it and know that at this magnetic strength, we see m/z equals whatever value. The output of the instrument is just a plot or a histogram of the ions that were counted at certain m/z values. So I'll give you an example here for a molecule of acetone. So the data looks something like this, where it's plotted with the x-axis being the m/z and the y-axis being given in relative intensity. So we'll often see mass spectra expressed in relative intensity, where instead of giving you the actual number of ions counted, it's kind of been normalized to the highest peak here to be the relative 100 intensity. So for the molecule of acetone, we do know its chemical formula, so we can use that to kind of think about exactly how mass spec works. Acetone is C3H6O, so we can quickly do some math here and figure out what the total mass of a molecule of acetone should be. Well, so the more common isotope of carbon is carbon 12, so 3 times 12, and then the more common isotope of hydrogen is just 1. carbon or hydrogen 1, 6 times 1. And then the more common isotope of oxygen is oxygen 16. So we have one of those times 16. Add all of that up, we get to 58 AMU, or atomic mass units. So then if you look at the data down here, what you're seeing is exactly this, a peak at 58 mass over charge. Right? So that tells you that something was measured with a mass of 58 over a charge of 1. So here we're going to focus on what's called low resolution mass spectrometry, and that means that really we're not dealing with the decimal points that might be detectable by better instrumentation. So in a high resolution instrument you would get decimal points that you would measure out. In our low resolution instruments you would not. So some features of the data are that because of the low resolution you only measure integer atomic mass units. So in all mass spectra, there will be a molecular ion peak. It's sometimes so small that you can't see it, but a molecular ion peak nonetheless is theoretically going to exist. And this molecular ion peak refers to the m over z signal here, which reflects the calculated or predicted AMUs of the molecule of interest. So for a molecule of acetone, that signal right here refers to this species. So the original molecule of acetone been hit by an electron beam and it's lost 1 electron, so now it becomes positively charged. This is what's actually detected by the mass spectrometer. That gives you 58 AMU divided by 1 plus charge overall, 58 m over z right here. So if you're looking very closely at this data, you might notice that there is this signal here at 58, but there's a tiny piece of signal here that seems to be showing up at 59. So something bigger than what it's calculated for the molecule. And so that might feel weird at first, because how could something be bigger than what I think I put into the instrument? Well, the reason for this is because there are isotopes of most elements that have different masses. So in most cases, those isotopes are heavier in mass. And so what we're seeing here is a small percentage of the acetone molecules that happen to contain an atom of a higher mass isotope. So in this case, the most common situation is that we would be comparing kind of our normal acetone of all the default or most common isotopes against a situation where one of the carbons happens to be the carbon-13 isotope instead. So 1 mass unit heavier, that gives you an expected m over z of 59. That's responsible for this signal down here. Of course, it could also be a molecule where, let's say, all the carbons are still carbon-12s, but the oxygen was oxygen-17. Or it could be that only the hydrogen, instead of being just 1 proton, was kind of the deuterium, or the twice as heavy isotope of hydrogen. Either way, it was some isotopically different version of acetone that is contributing to this signal. The last thing that you'll notice in this data is that there's a lot of signal at m over z values lower than the molecular ion, and those are coming from what's called fragmentation. It might make sense that if you're taking a molecule and subjecting it to a very high energy electron beam in order to ionize it, you might be putting in enough energy that bonds could break, and that's exactly what happens. So what you're seeing here are fragments of the molecular ion. So as the acetone is ionized, some of it is made into the molecular ion, some of it is broken apart into smaller pieces, and all of those will kind of show up in the ion beam and travel through the mass spectrometer. So an example of fragmentation looks like this, where you may start off kind of making the molecular ion, but then this kind of fragments into 2 pieces here. So in this case, kind of this exotic looking species right here, and then a methyl radical. And so if you do the math here, you'll get to an expected m over z of 43 for this ion, and that's exactly where you see this very large signal. So actually, at least under the conditions of this measurement, majority of what's detected is acetone in its fragmented form. Another important point is that we don't actually detect this species, methyl radical, because this is neutral. It is not an ion. We do not detect it. It is not deflected successfully by the magnet, so it does not ever get to the detector. And so given some mass spec data, we can kind of piece together these various components to try to figure out a chemical formula. So for now, we will focus on just the isotope patterns. We will in a future video look at fragmentation as it relates to mass spec. So again, the natural abundance of isotopes for all elements leads to the appearance of multiple signals, not just one single signal for the molecular ion. So there are kind of two useful types of isotope patterns that we're going to see. Some isotopes are considered the M+1, so one mass unit heavier than the more common isotope. And so some isotopes are considered the M+2 isotope, or 2 mass units heavier than the more abundant isotope. So we'll start off looking at the M+1 isotopes. Again, we just saw this with acetone, but the most common and useful one is that carbon-12 and carbon-13 are found in nature in approximately a 100 to 1.1 ratio. So if you're looking at a molecule of methane, you'd expect a molecular ion at 16 m/z, that's this large signal right here, and you'd expect an M+1 signal at m/z equals 17. And you can't see it really on the screen here, but there is a tiny little piece of red. And this should make sense because we should have a 100 to 1.1 ratio, so the signal should come around as 100 to 1.1 ratio. Nitrogen also has a heavier isotope. In this case, our normal is nitrogen 14 compared to the slightly heavier nitrogen 15. This ratio is now for every 100 nitrogen 14s, you're going to get about 0.4 nitrogen 15s in the environment. And so here's an example of this going on. So again, hard to see because this is such a small value, but we have our molecular ion at 31, m/z equals 31, and then a tiny little bit of signal if you're able to zoom in at m/z equals 32. The last M+1 isotope that's relevant to organic chemists is for sulfur. So sulfur 32 is in a 100 to 0.8 ratio with sulfur 33. So I'm going to show you some data here. And this one is actually a little bit more visible that there is the molecular ion at 48, that's nice and tall right here, and then there is detectable amount by the eye, at least, signal here at m/z equals 49. Now let's look at the M+2 isotopes. So the two halogens, chlorine and bromine, will be the most common ones that are seen. Turns out that chlorine 35 is in a 3 to 1 ratio with chlorine 37, and conveniently bromine 79 is in a 1 to 1 ratio with bromine 81. So let's take a look at some data. Here is the mass spec of chloromethane. And what's really nice is that with this 3 to 1 ratio, you can actually see it in the data. So at 100 relative intensity, that's the molecular ion at m/z equals 50. And at about 1/3 of that signal intensity, at m/z equals 52, that is the M+2 version of chloromethane. So same thing here for bromomethane. Here's the data, and you can see two very similarly sized peaks here, corresponding to a molecular ion and the M+2 peak. They aren't identical in height because, one, there is some amount of error when it comes to measuring these intensities, and two, actually, I lied a little bit, this ratio is more like 51 to 49 rather than exactly 1 to 1. Finally, it turns out that sulfur is kind of a complicated element. It also has an M+2 isotope. In this case, it's about 100 to 4.4. And that's part of why we are able to see some amount of signal here showing up at the M+2 or m/z equals 50 region of this spectrum. So that's great. It's easy to think about when there is one element that we're thinking about as existing in one isotope or the other. What happens when there's multiple elements within a molecule that can all be in varying and different isotopes? So there's two big things that we look for. So the M+1 signal intensity is usually used to figure out the number of carbon atoms that are in this molecule. And so if we kind of think about this probabilistically, again, we have this 100 to 1.1 ratio for carbon-12 to carbon-13. That means that for a carbon that you just randomly pick up on the street, you have a 0.0108 chance of finding a carbon-13 instead of finding a carbon-12. So for methane, again, our ratio is no surprise, right? 100 to 1.1 reflecting 100 to 1.1 here. All right, let's increase the number of carbons that we're dealing with. We'll look at ethane here, so just 2 carbons total. Now, because there's 2 carbons, you have to think about various combinations and probabilities of finding those carbon-13s. So if I have a bucket of ethane molecules and I go and try to pick one out and I look at it, well, there's a chance for both of the carbons to be carbon-12, for the right carbon to be carbon-13, or the left carbon to be carbon-13. And finally, there's also the chance for both carbons to be carbon-13. So the important thing here is that for the M+1 signal that we would expect for the mass spec of ethane, we have 2 different ways of obtaining that signal, which means that its signal intensity should be twice as big as the M+1 peak for methane. This is because when you're doing probabilities, we're kind of doing this is an OR situation, so then you can kind of just add up the 2 probabilities here. So 0.01 plus 0.01 gives you 0.02. I'm going to show you the math here. So again, if you have n number of carbons in a molecule, then there are going to be n ways to make the M+1 ion. And so then the math tells us that actually given mass spec data, so given the data here, so this fraction right here would be just the data that you extract from the instrument. You can take the intensity of the M+1 signal, divide that by the intensity of the M+ signal or the molecular ion signal, and divide all of that by 1.1. That gives you a nice estimate of the number of carbon atoms in that formula. Again, it's an estimate because the signal has some amount of error. There's other isotopes that contribute a little bit to M+1, etc. So you'll notice that I told you that ethane could have 2 carbon-13s and thus weigh 2 mass units heavier, 2 atomic mass units heavier than just regular ethane. But the chances of that happening are very low because you would need a 1% chance times a 1% chance to get both carbons to be carbon-13. So essentially it's negligible in the data. For chlorine and bromine, however, because the percentages are a little bit higher, it's much more probable for you to find the heavier isotope of those elements. Then compounds that have more than one halogen on them are going to exhibit what are called M+4, M+6, and M+8 signals. So let's look at a few examples. So I'm going to pull up chloromethane again, which we already saw, where there's just one halogen in the molecule. We should have a 3:1 ratio of the signals corresponding to molecular ion and the M+2, because that is the ratio of chlorine 35 to chlorine 37. Just to make this point clear, I will kind of label these here. So that tallest signal is the molecular ion. The next tallest one right there, at 1/3 the height, and that's the M+2 signal for the M+2 ion. And then finally, you might notice that there is still the M+1 signal. That makes sense, right? Because we have a carbon atom in the molecule, so there should be some amount of probability of having carbon-13 and chlorine 35. And along those same lines, there should be a chance of getting carbon-13 and chlorine 37, so an M+3 signal. Here, that's pretty negligible again because you kind of have 2 low probability events that need to happen in order for such a molecule to exist. So it does happen some small percentage of the time, just insignificant compared to the molecular ion itself. So once you have more chlorine atoms, then you're going to have a wider range of possibilities. And generally speaking, what you should get are, you always have a molecular ion, and then for each element or atom in your chemical formula that can add an M+2 signal, you would expect to see an additional kind of isotope pattern peak. So this is for the first chlorine M+2, this is for the second chlorine M+4, this is for the third chlorine M+6. Where kind of any one of the 3 chlorines being 37 atomic mass units would contribute to this signal. Having 2 out of the 3 being the heavier isotope will contribute to this signal. Having all 3 being the heaviest contributes to this signal. And so just in case that's not clear in the data here, the molecular ion is the tallest one, the M+2 is right there, then the M+4, and way down here is the M+6 signal. So I'm going to take a minute here to show you how to calculate these signal ratios. So the idea is to start off assuming you have just one signal and then to start to divide that up based on the ratio that's expected for the atom. So let's say I have a single chlorine. That means that for 4 molecules, really what I'm kind of doing is I'm saying that 3 out of 4 times I'm going to be going to the left or toward the lighter isotope. 1 out of 4 times I'm going to go toward the right or to the heavier isotope. So what I'm going to do is just take this blue 1 right here, which is the starting point, multiply that by 3 and on the left, and multiply that by 1 on the right. That gets me to the ratio I would expect for signals if there was 1 chlorine in the molecule, 3 to 1. That's exactly what we saw. If I add in a second chlorine, then what I do is I kind of think about, well, if I kind of have the lowest possible isotope, then for the second chlorine, again, it's kind of a 3 out of 4 times it's going to be paired with the red chlorine of the 35 AMU, and 1 out of the 4 times is going to be paired with the 37 red chlorine. And then if I'm over here at the purple chlorine 37, then I have the same kind of a ratio here, right? So the red chlorine with respect to the purple one could be 3 out of 4 times the lighter one, and then 1 out of 4 times the heavier one. And then we just go through and do this math. We get to 3 times 3 equals 9. In the middle, we have to be a little careful because we have 2 arrows pointed together. 3 times 1 is 3, plus 3 times 1 is also 3, so that gives us a 6 in the middle. And then 1 times 1 at the end gives us a 1. So for a molecule with just 2 chlorine atoms in it and no other halogens or anything else messing with the isotopes, you would expect this ratio of signals. Alright, finally we can introduce the third chlorine atom, and we'll do the same thing, right? So for each set we can kind of multiply our probabilities across like this. Gives us to 1 at the very far right where all of the chlorines are their heaviest isotope. In the middle here we're going to have a 6 plus 3. It's going to be 9. The next one over here where only 1 out of the 3 chlorines is the heavier isotope, it's going to be 9 plus 18. It's 27. And then finally all of the chlorines being the 35 isotope, that's going to be 9 times 3, which is also 27. So if you're looking at this, this actually is pretty close, right? The M plus, the molecular ion M plus and the M plus 2 signal are predicted to be about the same in intensity. That's what you have here. Those are then going to be about 3 times bigger than the M plus 4 signal right here. That's about what you see here. And then finally, they're going to be, from 27 to 1 is about 33-ish times, right? Approximately the ratio between the molecular ion and the M plus 6 peak. So if you're more comfortable with using just regular probability to figure this out, that's totally fine too. This is kind of just a different shortcut to doing it. If you do it this way, one thing you want to be careful of is that this is really easy when all of these are adding plus 2, because all 3 chlorines are doing the exact same thing. If for whatever reason you're dealing with, let's say, chlorine in the purple row, but then the carbon in the red row, then these arrows don't line up. So you do want to keep in mind what the actual kind of spacing is here, that this is giving you a -1 and a +1 here, and that those are overlapping. At least in this case, that may not always be the case. Okay, so that was kind of given mass spec data, how do we interpret it and kind of analyze it to match the molecule that we know the data is from. The more challenging and more interesting part of using mass spec data is to take a piece of given data and try to figure out what formula that data even corresponds to. So we'll try to do that here for an example, but I'll walk you through the steps. So the first thing you always want to do is to try to figure out the number of carbons you might have, again an estimate of the number of carbons, using that kind of a 100 to 1 ratio rule. You'll want to determine if there are either an odd number or an even number of nitrogen atoms using what's called the nitrogen rule. And this is some interesting math that just happens to work out really nicely, but if your molecular ion is odd, then you will have an odd number of nitrogen atoms in your chemical formula. If your molecular ion is even, then you'll have either 0 or 2 or 4 or whatever even number of nitrogen atoms in your chemical formula. So that's a really neat way to figure out nitrogens. Next, you'll want to look for if there's any kind of M+2 indication of sulfur, chlorine, or bromine existing. And once you do that, you actually can account for a lot of the mass that you've detected at the molecular ion. And from there, it is a little bit of guess and check to fill in the missing masses that you don't know about. So let's look at an example here. This is I guess a table form of mass spec data. So I'm just kind of telling you that at m/z61 you have the intensity relatively of 100, 62 m/z you have this tiny signal 1.5, and then at 63 it's even smaller at 0.4. So when I look at this, what I'm seeing right away is that the M+2 signal is pretty insignificant here, right? So for step 3 here. So that tells me that there's probably no chlorine, bromine, sulfur. Okay. Then I'm also going to look at the M+1 signal, do my estimate of number of carbon atoms. So I take that 1.5, and because this is already set to 100 here, I can kind of do my math really easily. So I can just take this and do 1.5 by 1.1. So the 1.1 coming from the carbon 13 to carbon 12 ratio. And if I do that, I get 1.4, or 1.36, I guess, carbon atoms. And whenever this happens, where you get a non-integer number of carbon atoms, we always round down because there's other things that can contribute to increasing this relative intensity, much less likely for the intensity to be underestimating. It's always going to overestimate your number of carbons. So this tells us we have one carbon atom in our formula. And then we have the nitrogen rule here, and so clearly we're dealing with an odd molecular ion, and so that tells us we should have kind of 1, 3, 5, etc. nitrogen atoms, right? So we don't know right now if it's 1, 3, or 5. That's actually a lot of information. So what we want to do now is to try to figure out how much mass we've accounted for and how much we're missing. So we start off just by using our knowns, right? So we can kind of make a table here. All of our organic molecules will look like this, right? We have a carbon. In this case, we know we have a nitrogen. We may have hydrogen. We may have oxygen. We don't have chlorine, bromine, or sulfur. Right now, I'm operating under the assumption that I have one carbon. We'll start off with the assumption that we have one nitrogen. If that's the case, we are missing how much here? So this would be 61 minus 26, so 35 mass units. You can imagine doing something like this, right? I could just go in and write in 35 hydrogens to account for all 35 of those and 0 oxygens. This should immediately strike you as unreasonable. There's no way to have a molecule with 1 carbon, 1 nitrogen, and 35 hydrogens, right? So this is just an unreasonable guess. Let me start over here. Let's say I have 1 carbon, 1 nitrogen. If I know that oxygen has this mass of 16, that can help me a lot towards getting rid of or accounting for this amount of mass right here. So let's say I put in 1 oxygen. That is 16. That still leaves me with 19 hydrogens. This still doesn't seem reasonable to have 19 hydrogens versus just 1 carbon, 1 nitrogen, 1 oxygen. No way you could draw a valid Lewis structure for that. Okay, and I'll cross that off. Okay, so then we'll try 1 carbon, 1 nitrogen, maybe 2 oxygens. Then that leaves us with 3 hydrogens. Now this is starting to look more like a reasonable chemical formula, right? So this might be reasonable. So this kind of looks like this, right? CH3 and O2. You can kind of actually be able to draw a structure from this right away because this kind of looks like a methyl group and a nitro group. But it's important to make sure whether or not other possibilities exist. So with mass spec, there are often various different formulas that will fit the data that you've collected. So why don't we go back and see if we could do 1 carbon and 3 nitrogens. So that is kind of 12 plus 3 times 14. That is equal to 54 total. And that would mean that I need to account for 7 hydrogens missing with 0 oxygens, and that seems pretty reasonable, right? So you might have a formula that looks like this instead. And that would also be a valid explanation for what's going on in this data. Finally, we should always go back and just double check that everything makes sense. So when we were looking at the m+1, we had noticed that this value was a little bit higher than the 1.1 we might have expected for just having 1 carbon. If you recall the isotope pattern for nitrogen, well, nitrogen has about 0.4 to 100 of the heavier isotope of nitrogen. And so that conveniently works out to be the missing piece here between 1.1 and 1.5, right? So I would expect then, or predict, that based on this data, it makes a little more sense for me to go with the first formula because the nitrogen isotope pattern seems to do a better job of matching what was actually reported in the data. So we'll say that this is our best option. So hopefully that gives you a sense of how mass spectrometry works, how the data is collected, interpreted, and then finally how to use mass spec data to try to arrive at a chemical formula.